Welcome back. COL 774 is machine learning, and today is April 14th, 2020. Okay, so last class, remember, we were looking at, right, we completed deep neural networks, right, um, and then we started our exposition of unsupervised learning, right, and recall that unsupervised learning, which will be the topic for next few weeks, essentially dealt with the setting where, you know, in the supervised setting we had these instances xi yi, I equal to 1 to m, and in the unsupervised case this yi's are missing, right? In other words, given only the instances, right, or their features I going from 1 to m, we want to do something useful. We want to learn some useful patterns in the absence of any class labels. Okay, and we looked at three different ways of doing unsupervised learning, or in particular three different sort of dimensions that we will look at. The first one was clustering, right, and in this context we will study a means algorithm, line here, right? That will be the topic for today and be part of the next class. And then we said we will look at density estimation, and in that context we will look at GMM, Gaussian mixture models, or rather this GMM leading to an algorithm called EM, which is expectation maximization. And the last thing that we will do on this topic is principal component analysis, which is also referred to as PCA, right? This is about dimensionality reduction. Great. And let me write here for completeness, this is Gaussian mixture models, and EM stands for expectation maximization, right? And we went into sort of broad overview of each of these topics in the last class, right? So without spending much time on further sort of um, broad intuition, let us dive directly into the k-means algorithm. Okay, so k-means algorithm, this is what we'll study in the context of clustering, right? So our goal is to understand clustering, and specifically we will study the k-means algorithm, and we will keep this diagram along with us for the intuition, right? So this is in the 2D space, but in general we will be working with any space which is in Rn. So given some data points I equal to 1 to m, each xi belongs to Rn, right? We would like to figure out, our objective would be to figure out these for all I, these Ci's, right, and which belong to this discrete set 1 to k, which are essentially your cluster assignments, right? So this is our objective, and we will assume that the number of clusters, which is k, is known to us a priori. Right, so this is a very simple setting, right, where we are given these data points xi I equal to 1 to m, no class labels, right? Only features are given for these points. And for each point, we would like to find a cluster assignment where each cluster assignment variable belongs to a discrete set which is from 1 to k, right? And there are other clustering algorithms which are more general in the sense that they will discover the number of clusters on the go, but that's slightly more advanced, and maybe I'll refer to some of those at the end of this class, or when we finish K-means. Right, and we already talked about intuition, but this is an important problem because often you will get data, let's say, right, it could be, um, you know, your customers in a market segment, or students in an institution, or maybe biology, it could be proteins, and you would like to sort of categorize them or separate them out into multiple such clusters, right? Okay, and for to build the intuition, we'll work with this 2D diagram where this is sort of the feature 1 and feature 2, x1 and x2. Right, you can think of the monkeys and chimpanzees example here, also where x1 was weight and x2 was height, and we were looking for clusterings which essentially, right, or intuitively were could separate these points into two different clusters, right? And the entire sort of goal in this class would be to really formalize this notion of what is this good cluster, right? Why would we draw uh, boxes like the ones in the blue, and maybe not the boxes like this, right? And most of us would agree that the clustering which is represented in the blue is probably a better clustering, and that's what we will really try to formalize, right? So let me sort of erase this. Okay, and to do this, to be able to do this, we will introduce another set of variables which will be referred to as cluster means, and these will be mu1 to mu k, right? And each of these mu1 to mu k, let us denote by mu l, will belong to Rn, right? So we have these uh, k variables, right? One for each cluster, which will refer to which we will refer to as cluster representatives, right? And they are sort of in the Rn space, right? For example, in this case, the cluster representatives intuitively would be a point here, which is, let's say, mu1, right, which is the representative for cluster 1, and there could be a point here mu2, which could be your representative for cluster 2, right? This is your cluster 1 and this is your cluster 2, right? And these cluster representatives will play a very important role in figuring out the right set of right, right? Note that these are continuous variables, and the cluster assignments are sort of discrete way, right? And given this setting, let me sort of write the objective, uh, right? And then I will give you the intuition. The objective that we will try to optimize will be for every point, right? We will try to minimize its distance from the corresponding cluster representative, right? So you take mu ci is essentially the cluster assignment for point I, and what we really would like to do is we would like to minimize this square distance over all the points, right? So take each point xi, and essentially what we are looking for is a cluster assignment and a set of cluster centroids, such that the distance of the sum of the distances of the point xi from its representative mu ci is minimized. right? And before we go any further to develop this intuition further, I would like to mention this norm, right? So given a vector u, right, in Rn, recall that this norm vector, square of the norm, is simply defined as uj square sum over j equal to 1 to n, and right, so the norm is half of this, and then if you do a square, then this is the square of the norm, right? So this quantity is essentially a norm of u, right? And in the Euclidean space, right, this two norm is essentially the distance of this point from right, it's just the length of the vector, or if you are sort of in the 2D space or n dimensional space, you can also think of it the distance of this point from the origin. um, okay, and this is sort of the square of the norm, right? And there is a generalization of this to p norm, but let's not go. Okay, so given this, what is our goal? Our goal is to really sort of optimize this objective, and let us try to understand the intuition, right? And maybe let me do that on the next slide. Right, so let me draw that picture again, right? So these were our points in the 2D space, and this was our function, right? Xi minus mu ci square, right, which was 2 norm square, and this 2, the subscript 2 is often sort of omitted, right? This is what we wanted to minimize, and we will often write it as j c mu, right? So this is our optimization metric, we will, and we want to minimize this, right, with respect to mu and c, or c and mu. uh, okay. uh, I will just make it mu c to be sort of consistent everywhere. So just make it mu and c, right? Just to follow a uniform sort of notation, right? So this is our j of mu and c. Okay, so now I have given you a bunch of this sort of mathematics and maybe complicated looking expression, but let us try to understand the intuition behind discovering this cluster. Right, and as we saw on the previous sort of diagram, this is maybe the clustering that we are looking at, and not the red one that I sort of drew on the previous slide, right? And what is the intuition, right? So what is the right? So the question that we would like to ask is, what is a good clustering, right? And intuitively, right, a good clustering is the one, right, which is also demonstrated by the one on the top left here, is something which satisfies the following objectives. The first one is that the distance between the points within a cluster should be minimized, right? In other words, we are looking for an assignment of points to cluster, so that all the points within a cluster are close to each other, right? So this is a different way of saying that distance of points within a cluster is minimized, right? In other words, the points within a cluster are close to each other. The second one would be distance of points belonging to different clusters should be maximized, right? This is a different way of saying that points which belong to different clusters should be as far apart as possible, right? So this is sort of the objective, that intuitively, when we say something is a good clustering, we are saying that the points which are in the same cluster have affinity with each other, right? And they are really sort of close to each other under some given distance metric. and points which are sort of in different clusters, right? They are different from each other. Right? Therefore, that's why they're in different clusters, and they should be sort of far apart, right? So this is our intuition of a good clustering, and we will see that this sort of JC mu that I've written here is really trying to formalize this intuition mathematically. And let's spend a minute or so trying to understand why this captures this sort of intuition, right? This particular metric. In other words, right, if we could minimize or optimize this metric over mu and c, right, then we would sort of get the right clustering. This is because, right, what we are saying is that we want to minimize this xi minus mu ci, right? And what is mu ci? Mu ci is simply the cluster representative for point I, right? And what we are saying is that, right, that for every uh, point in cluster, in a given cluster, right, the distance of that point from the cluster representative should be as minimum as possible, right? And we are sort of summing over all the points. In fact, that is an important thing that I forgot. This is sum over I equal to 1, right? So this is not for a specific I, but sum over all points, right? And just by ensuring that each point is as close to its cluster representative as possible, right? We implicitly sort of also satisfy, right? We satisfy both the criteria, that is the points within a cluster should be close to each other, which is explicitly satisfied or explicitly enforced by this metric. But by virtue of doing this for every sort of point, right, in the space, that they should be close to the respective cluster representatives, right? We will also be able to achieve that the points in different clusters are far, right? And I'll encourage you to sort of think more about that intuition. Okay, and right, so just going a little bit ahead of us, right, we will see that our sort of objective here is to determine, right, for all I, these CIs where each CI belongs to this discrete set, right, which is 1 to k, and also for all L, right, mu L, right, where mu L belongs to R, right? So this is our optimization problem, where this is sort of a discrete optimization problem or discrete set of variables, and this is a continuous set of variables, right? And we would like to optimize this JC mu over J mu C, rather, over these two sets of. And going a little bit ahead of ourselves, we will see that each of these CI will be nothing but argmin over all possible uh, uh, argmin over all possible cluster assignments L and xi minus mu L. Right. Essentially, what we are saying is that you assign point xi to that cluster L, whose representative is closest to that point, right? And that makes sense. And similarly, right, we will see that mu L will simply be the mean of those points whose cluster, right, which belong to this cluster, right? So all Ci such that all xi such that the corresponding ci is L, we sort of take sum of them, right? So sum over I equal to 1 to m, indicator of ci equal to L, right, which is essentially like essentially selecting the points belonging to cluster L and taking a mean over those xi's. Right? So this will be our mu L, and we will sort of formally derive this, right? But I just wanted to give you sort of a look ahead that the CIs will simply be the assignments which sort of bring the corresponding cluster representative closest, right? It'll choose that cluster assignment which is closest to xi, and the cluster representatives will be sort of the mean of those points which belong to this cluster, right? And in fact, this sort of whole expressions, right, uh, also will give us the idea to sort of derive the algorithm which is k-means algorithm. Okay, so now let us try to understand sort of the derivation of k-means algorithm, um, right? And then let me sort of explain again, because because I've changed the slide, right? And the whole idea, right, in k-means algorithm is as follows, right? Suppose we knew what the mu's were, then we could really figure out what the optimum C's are, right? So what it is saying is that, right, and this will be sort of part A, that if we knew, right, what the cluster centroids were, right? So if someone told me that this is sort of your mu1, which is representative of our cluster 1, and this is your mu2, which is the representative for cluster 2, then it will not be very difficult to figure out the cluster assignments. And why is that? Because once we have the representatives, then we can simply choose those points, right, which are sort of or rather we would choose for every point that cluster whose representative is closest to that. Okay, and similarly, right, suppose, right, we knew what C's were, right? Suppose we knew, which point belonged to which cluster, and I'll show it in the diagram, then essentially we could figure out the optimal assignments for or optimal mu's, right? So if we really uh, knew, what which cluster each point belong to, right? So in this case, this could be, let's say, uh, two different clusters, right? Let's say maybe these points here belong to cluster 1, and the points here belong to cluster 2, right? If someone really gave me this assignment, then I could essentially figure out mu1 and mu2. And what will those be? Right, those will essentially be, because they are representatives, we will formally see, right, these will be sort of points which represent the entire cluster, and we will see that those are exactly the means or the centroid, right? So what this analysis is just saying essentially is that that the problem is not that difficult, um, if we sort of um, look at solving this alternatively, that if we knew what mu's are, then we will be able to figure out what c's are, and if we knew what c's are, then we will be able to figure out what mu's are. And this is essentially the schematic of the key means algorithm, right, which sort of goes back and forth between trying to optimize this for these mu's and c's, right? And there is one thing that I really wanted to sort of point out here, is that if I look at the original objective, which is j mu c, which was xi minus mu ci, right, whole square, and sum over I equal to 1 to m, right? By itself, it is right a difficult problem, right? Because this is a mix of discrete plus continuous optimization uh, problems, right? So there is a uh, sort of a discrete optimization over C's and continuous optimization over mu L's, and directly sort of optimizing this is difficult, and this is why we essentially have this two-pronged strategy of figuring out C's given the mu's, which is sort of A, and we'll look at it later in the context of AMMs. This will be essentially our E step, figuring out the cluster assignments given the centroids, and then in the B step, right, which we will refer to as M step, right, I'll explain them later, will be figuring out the parameters or the mu's given the cluster assignment. Okay, so now let us try to figure out the details of each of these steps, A and B, right? That will essentially give us the desired sort of values of the variables. This is step A, and this is B. So this was, you know, given uh, given mu's, figure out C's, and let me draw a sort of a line here, right? Let me see if we can draw it better. Okay, great. And what is the sort of the B step is given the C's, figure out what mu's should be. Okay. Okay. Now let us look at the expression. The expression we had was J mu C was given by uh, xi minus mu ci square I equal to 1 to m, right? And in other sort of words, right, what we are looking for is argmin over, right? So we want to minimize this jc mu with respect to mu and c, but mu's are given to us, right? So essentially in this step, what we are looking for is argmin over c's of xi minus mu ci whole square, right? And right, this is equivalent to argmin over c1 up to cm of xi minus mu ci whole square, right? And if you right, and there is a sum here all through, right? And if you look at it carefully, right, the ci only depends on xi, right? And which makes sense, right? And this is all given that we know the mu's, right? We know the cluster representatives, which is equivalent to saying that for all I, right, we want to figure out, what is the value of ci, right, which minimize xi minus mu ci whole square, right? And this is sort of a discrete optimization problem because each ci can take values from 1 to k, and this is exactly ci would be the cluster whose representative would be is closest to xi, right? Right, the solution to this discrete optimization problem is simply for each ci, right, we assign that cluster index, right, whose mu right is closest to point xi, right? And this is not very difficult to verify. Okay, very good, right? So this is fine. Now let us look at optimizing j mu c, right, which is again I equal to 1 to m xi minus mu ci whole square, right? And in this case, because we are trying to figure out mu's given c's, right? Therefore, equivalently, that we want to minimize j mu c. Therefore, equivalently, we want to do argmin over mu's this time of j mu c, which is xi minus mu ci whole square I equal to 1 to m. Okay, and breaking this apart into mu1 up to mu k I equal to 1 to m xi minus mu ci, right? And what we can do is that this is equivalent to writing or optimizing the following problem, which is I equal to 1 to m and indicator of Ci equal to L and Xi minus mu L square and sum over all possible L, where L equal to 1 to capital Q. Okay, and this particular way of writing things gives us an idea that we can separate out this optimization for all each of these L's, mu L's, by writing for all L we are looking for minimizing mu L uh, you know over mu L, the following expression, which is I equal to 1 to m, and right, this indicator of those points for which the cluster representative index is L, and then xi minus mu L norm square, right? And this is sort of the final expression, right? And let me sort of deal with this in the on the next slide, right? So this is just one last sort of remaining step from the previous slide, which is simply saying that for all L, this is in the step B, which is determining mu's given C's for all L. We are looking for argmin over mu L, indicator of Ci equal to L xi minus mu L square and sum over all possible examples, right? And this is homework for you to right. This is a optimization problem in right these sort of single set of variables mu l's, right, where each, recall that each mu L belongs to Rn, right? And we can solve this by simply taking gradient with respect to the vector mu L, and this homework for you to show that that the optimal value of mu L, right, which sort of minimizes this, is exactly the mean of the corresponding data points, right? So this will be indicator of Ci equal to L xi I equal to 1 to m, right? And then right, because this is the mean, right, we will simply divide by uh, number of points belonging to that particular cluster. Great. Right, and in this process, right, what we have discovered essentially is the k-means algorithm, right, which is sort of optimizing this two-step process of um, right, given the mu's optimize c's and given C is optimized for muse, right? And let me describe this more formally on the next page. And before we go to the next page, next slide, right? This sort of doing this alternatively would have optimized our original sort of function, which is j mu c and min over mu and c, right? Arg min over um, mu c will give us the corresponding values, right? Or we can say min over mu c, which is sort of the minimization of this. Uh, so just a small clarification, minor clarification from the previous slide, that our objective is j mu c and we want to minimize over mu and c, right? So this sort of minimizes our objective, but essentially what we are interested in is those values of mu c, right, which obtain this minimum value, right? So these are sort of two equivalent problems, right? We can minimize the objective, but here, more than minimizing the objective itself, or finding the optimum value of the objective j mu c, what we are really interested is in these values of these mu and c variables, which will essentially give us the, but in terms of actually solving the optimization problem, they are more one and the same. They are one and the same thing. Okay. uh, okay, so now let me describe the k-means algorithm slightly more formally, right? So this is our k-means algorithm, right, which takes in a bunch of data points I equal to 1 to m, right, and each xi belongs to some n-dimensional space, right? And this k-means algorithm proceeds in the following manner, right? So there is this mu zero, which is mu's at time step zero, and you initialize them, right? We'll talk about that, how to initialize them in the beginning, right? These are essentially your cluster representatives or cluster centroids, or cluster means, for the reason that we saw, the values of these mu's will actually be eventually the means of the points belonging to each cluster, right? So t goes to 0, and then we repeat this process do and until convergence, right? And what is this process? This process is exactly the sort of two-step optimization, right? Where the sort of the a step, which is also sort of the e step, is nothing but we want to essentially assign our c's, right? Given the mu's, right? We want to find the assignment for we want to find these cluster assignments, which is nothing but r min over c's of xi minus mu ci whole square, right? And so this is step A, and then the step B would be simply given your new cluster assignments, right? C's. Now we want to find those mu's cluster representatives, which again sort of minimize this quantity, but now with respect to mu's, right? And we sort of repeat this process until convergence. Right, so just let us look at this expression again, right? What is this A step, which is also referred to as sort of the E step, right? Or computing expectations, and right, I will that will become more clear why we call it computing expectations, right? But just remember that finding these cluster assignments is referred to also as sort of the E step, and there is this M step, which is the maximization step, which is finding these uh, mu's, Note that here this step B is written as a minimization of this distance, but later we will see this that this can equivalently be written in form of a equivalent sort of a maximization problem over some kind of likelihood, but let's wait for that, right? And this will be in the context of GMM and expectation maximization, right? So for now, this is simply step A, which is argmin over C of xi minus mu ci, right? So what is it saying? That given the current set of parameters, right, give me the cluster assignment, right, which is the best in terms of minimizing my optimization metric, which is xi minus mu ci, right? And in fact, very important, I again forgot to put this sum here, right? And this sum here, right? Right. So this is the step A, which is finding the cluster assignments given the mu's, right? Using the expression that we saw on the previous page. And the step B says that once you have updated your cluster assignment, now give me, the better or sort of the next set of parameters, which optimize this objective given the new cluster assignment, right? So every time we sort of employ this step A and B, we are looking for the most recent um, the parameters or the cluster assignments for computing. So let me say it again, right? At each step, right? For example, for step A, we are looking for the most recent mu's to compute the new C's or the cluster assignment, and in step B, we are looking for the most recent cluster assignments to compute the new mu. Right? And this process sort of goes on and on until sort of convergence. Right, so let me just write here, this is sort of the iteration number, t goes to t plus 1, right? And I should say that I have not really used t here in the step A and B, just to avoid cluttering of the notation. But if you were to do it more formally, right, 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 you would sort of index the RHS and LHS appropriately with t or t plus 1, right, which is basically the parameters, that is mu's or the cluster assignments at a particular times, right? But I want to mention one more thing, which is what is this convergence, right? So how do we detect convergence? So in this case, as it turns out, that the convergence is essentially you can it's a two-step process that you can check whether if there is any change in no change, right, in the cluster assignments, right, which will also equivalently mean that there is no change in mu's, right? So any iteration, right, where essentially the cluster assignments and 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 the mu's, right? So in right, to keep it simple, right, any iteration where the C's have not changed and correspondingly the mu's have not changed, we will say the algorithm is converged, right? And my last point about the convergence of this algorithm, right? So this is sort of your k-means algorithm, and this k-means algorithm is guaranteed to converge, right? Let me use a different pen, right? This algorithm converges to local optimum of J mu C function, right? And what is the sort of the local optimum of this, right? This is a mix of discrete and continuous optimization problem, right? So here local optimum can be thought of as there is a sort of no better clustering in the immediate neighborhood, right? So in particular, if I change the mu's a little bit, um, right, or right, if I change the C's a little bit, right, if I change perturb the either the centroids a little bit, centroids a little bit, or the cluster assignments a little bit, meaning if I move one point from one cluster to another, then there is no better clustering in that neighborhood, right? So in that sense, right, this entire algorithm, k-means algorithm, converges to the local optimum of this k-mu. So last thing that I want to do before we uh, break this class is actually to work out an example of working of this k-means algorithm, right? So let's say these are sort of your data points, right, which have been given to you, and in step equal to 0, right, this will be your init assignment, right? So you will, right, given these data points, you will try to figure out what mu1 and mu2 are, and let's say someone tells you that this is your mu1 and this is your mu2 at time step equal to 0, right? So this is your sort of initial cluster representatives, right? And then in the next step, which is at t equal to 1, uh, you will now try to first find out your uh, cluster assignments given these cluster representatives, right? And it is not very difficult to see that your new cluster assignments will be given, by this line, which separates out points on the left side to be in cluster one and points on the right side to be in cluster two, and this is in some sense a bisector of the line, you know um, joining mu1 and mu2, right? Because right, points in the cluster 1 will be closest to mu1, and points in cluster 2 will be closest to mu2, right? So this is a sort of your clustering at time step t equal to 1, right? And then given this, right, the next step would be at equal to 1 would be to figure out your new cluster representatives, right, given these clusters, given these cluster assignments, right, which will mean that, right, if you look at the points again, then what is going to happen is that mu1 and mu2, both of them will move slightly to the right, right, because the mean of the points in sort of the, the left cluster is probably somewhere here, right? So this will be your mu1, mu1, and right, probably your mu2 will again move to the right, because now it is computing the mean of the points in this second cluster, right? So this will be your sort of new mu2, right? So this will be at iteration t equal to 1, right? And then taking this process forward, right, to save some space, let me draw at t equal to 2. What happens is that now you want to figure out your new cluster assignments again based on this new mu1 and new mu2. And what is going to happen is, right, we draw these points again, right, and these points again, right? And this time your decision boundary will almost classify all your points correctly. Maybe there are a few points remaining which are sort of in the wrong cluster, but mostly, right, this is cluster 1 and this is cluster 2, and this is sort of again based on bisecting the line between mu1 and mu2, right? So the cluster 1 has now the points which are closest to new mu1, and cluster 2 has points which are closest to new mu2, right? And correspondingly, right, again in step equal to 2, we are going to now figure out our new mu1 and mu2, right? So these are the points drawn again, and this time around, your mu1 will almost be where it should be, right? As we'll say, it would have almost converged, and this will be your mu2, right? This is your mu1 and this is your mu2, which is are the means of respective um, points in respective clusters, right? And then what happens at t equal to 3 is when we compute the new cluster assignments, right? Given this mu1 and mu2, it will look something like uh, these are the points uh, in the two, right? These are the points, and now, right, if we look at mu1 and mu2 and sort of the bisector of this will be our separator, and these will be points in cluster 1 and these will be points in cluster 2, and correspondingly we would have uh, the cluster uh, representatives mu1 and mu2, which will essentially be the points here and points here, right? And mu1 and mu2 would be somewhere here, mu1 and mu2, right? This is the time t equal to 3. And right, I'm not drawing it any further, but it is not very difficult to see that in the next iteration, that is at t equal to 4, right, the algorithm would have converged, because right, in the next step we will not see any change in the cluster assignment, right? The clusters 1 and 2, right, that will compute based on the latest mu1 and mu2 will be identical to the previous clustering at time step equal to 3, and hence the mu1 and mu2 will also not change from t equal to 3 to 2 equal to 4, t equal to 3 to t equal to 4, and therefore algorithm would have converged in 4 steps. Uh, uh, One final remark that I want to make about choosing initial mu else is that when you actually implement this algorithm, then you should choose mu else to be choose them to be one among the data points, right? And this is really important, because that gives you uh, excise, right? That is really important because that gives us some grounding into the data, right? If you choose them arbitrarily in sort of the Rn space, then algorithm may have very difficult time conversion, right? And think about more why that may be an issue, right? But from a practical standpoint of view, it is very important that the initial sort of centroids are chosen, right? You can choose them randomly, but they it is better, right? It is important to choose them to be one of the points which are actually one of your data, right? And finally, right, in next class we will look at failure cases of k-means algorithm, right? Cases where k-means algorithm does not work very well, right? It does not give, clustering which is sort of intuitive clustering, and that will lead us to the next sort of algorithm, which will be, about density estimation, but clustering will fall out as a byproduct of this, which will be GMM or Gaussian mixture models, right? And this will eventually lead us to study a very important algorithm which is referred to as expectation maximization. Okay, let me stop here and I will continue in the next.